This is going to be a quick video lesson on capacitance. This is not like a homework thing. I want to do more of these lesson videos. So hopefully you can learn something from this rather than, get homework answers. But intro to capacitance, we're going to talk about what a capacitor is, what does it do, and how does it affect a circuit. A capacitor really, by basic definition, is just a device that stores charge. And by consequence of storing charge, right, it's also storing electrical potential energy because there's going to be some electrical potential energy with the charge being stored. So by consequence of storing charge, it also stores electrical potential energy. And that energy can be used, right? So I'll talk about more about energy in a second, actually, and what I mean by the energy can be used. Let's just get a circuit going. We're going to talk about this circuit in a second, but the most simple circuit with a capacitor is just the battery and the capacitor. So you might be saying, what in the world is that capacitor? If you take a capacitor, so if you go to school and you take a capacitor, it looks, it kind of looks like this, so I don't really know how to draw it. Kind of looks like that, and then you take your little wires and you hook it up to these metal thingies. Really, inside of this capacitor, if you were to dissect it, it would likely have two conductive sheets of metal or something, and they're going to be separated like this, right? If you look at the top down, these two sheets are separated with something in the middle. Usually there's paper or something in the middle. And a capacitor doesn't really need that. It could actually have nothing in the middle. So if I were to draw a 3D view of this, it would look, I guess, something like this. And then, yeah, so it would look, I don't know if this is a 3D view, something like that. I don't like that way. Let me make that a real battery. So this is a 3D view of the two sheets that I'm talking about. They don't need to have anything in the middle, but we're going to learn in the future, I'm not going to talk about in this video, if you actually put something in the video, it allows it to store more charge compared to without. We'll talk about why that is in much later into the unit, but you can also have nothing in it. That's what I'm trying to get at. Usually you won't have nothing, but you can. Air is in the middle, in real life, but that can actually be treated basically as nothing, and we'll talk about why. This is the most simple circuit you can get. So, how does it work? Well, when you connect it initially, there's going to be, and electrons are the ones doing them. Actually, yeah, I'll explain in terms of electrons first, just to better conceptualize. Electrons will flow through here, right, from the negative terminal. So I'll have electrons flowing through here. There will be some current. And eventually what will happen is one negative, right, the first negative that comes out of here, whatever, is going to get essentially blocked by this plate, right, because it can't jump over and continue the circuit. It's going to get blocked by this plate, stop there, but what's going to happen after that is there's going to be a very small kind of electric field. Now, this electric field actually would point towards the negative. And this small electric field, guess what? The charges on this plate are going to get affected by that field. What charge is going to get repelled by the negative? It's going to be another negative. So another negative is actually going to move out of that plate and will basically complete the circuit, right? Because negative comes over here, negative moves out here and gets back to the battery. Hey, your circuit's complete. So negatives, let's say that one negative will come back in here, but as more and more negatives build up on this plate, there's a stronger and stronger electric field. So more and more negatives are going to want to leave that plate. And what eventually happens is the amount of negatives that enter this plate are the same amount of negatives leaving that plate. And when you have negatives leaving the plate, you get positive charge on that plate because the positives are fixed in place. So the plate here, I'm drawing negatives to show that they're leaving, but really it'll end up being positive. And it'll be the same amount of positive charge and negative charge. Positive charge here is the same amount of negative charge there. So if this is Q, this plate would have negative Q. Why? But it comes back to that idea of the amount of electrons that come to this plate is equal to the number of electrons that leave the left plate. So the amount of negatives that leave this plate, same amount of positives, so the positive and negatives, they're the same. Okay, so there's no resistor in this circuit. Like, this is not a resistor. It's a whole other thing. It's a capacitor. It doesn't resist the flow of current. It's just storing charge. There's no resistor in this circuit. So if these wires are like your resistor, they have zero resistance. So tie it back to Ohm's law. V equals IR. Well, it's like this is equal to, like, I don't know, 10 volts, right? The battery. But the resistance is 0. So it's like, mathematically speaking, this should be like infinity, right? Because it's like 0 times infinity. Or if you think about it as like divide both sides by R. If the resistance of the wires is 0, it's like you're getting infinite current. So really what's happening is as soon as you connect it, there's infinite current. It's going to immediately, all the current's just going to flow in, charge the capacitor like instantly. If you don't have a resistor in there. In real life, the wires do have some resistance, but it's very small. So if you have a very small resistance, you get a really large current. That thing's going to charge up really quickly. Now, if you have a resistor in there that's resisting the flow of current, it's going to, if you use Ohm's law, right? It won't be infinite current. The current will take its time to reach the capacitor. Same physics applies though, right? I was talking about the movement of negatives, but you could think about it in the same way with positives. Positive comes through here. As soon as a positive lands here, a positive repels and you're left with a negative. And eventually you're going to get that equal opposite buildup. So this is an important key concept. At the instant the instant you connect the battery to the circuit, right? The instant that you hook this circuit up with the voltage, one positive is going to leave, positive comes here, and one positive is going to head back in. That's a complete circuit. And in fact, you can treat it for that very instant that you hook it up to the battery, you can treat the capacitor like it's not even there. So if you just, like, T equals 0, right? The instant you plug in this battery, the capacitor is not even doing anything. Ohm's law still applies. Like, you could find the voltage, or you could find the current through the circuit by just doing V equals IR. That capacitor is not having any effect on your circuit because for that one instant, the positive is freely able to move here and then one positive is freely able to move out. What's eventually going to happen is as more and more positives build up, there are going to be more like the positives coming through this battery, they're going to be like, whoa, there's a repulsive force, right? I can't move over there, but then I can't move over here because there's more positives here. The circuit stops, the current stops, right? It's going to like kind of slow down by this repulsive force and then just come to a halt. If you saw the demo in class, when you hooked up the battery and the light bulb and the capacitor, there was initially light, like initially current and power, but over time as this got charged up, the current slowed down and the light bulb dimmed down. That's why. It's because of this buildup on this charge. This is one way to also think about it. I'm not sure if the physics is like 100% correct. This is just the way that makes sense to me. But current is caused by a potential difference. So initially, there's no like potential at this point because there's no charge being built up. So if I kind of get this, I'll use this circuit because it's just clean. But like the instant that I connect this up, there's no charge here. And I know that potential is equal to KQ over R. No charge means no potential. So there's high potential here and no potential here. Potential difference, current is going to flow. And we're going to have, so let's say a positive ends up here. Now, when the second positive is heading over here, there's now a little bit of potential. So the potential of the battery, right, if you think about the potential difference, like potential battery minus potential capacitor, if the potential of the capacitor got bigger, there's less potential difference. So the current is going to kind of slow down. And as you get more and more and more and more and more and more and more charge building up, and remember we have the same amount of negatives on this side because the positives were leaving, as this gets bigger and bigger and bigger, the change in potential is going to get smaller and smaller and smaller, and eventually it's going to get to zero. So think about your ponds. If there's no potential difference, if the top pond is equal to the bottom pond, no water is going to flow, no more current is going to flow through the circuit. And if we think about voltage of the battery is equal minus voltage of the capacitor equals zero, hey, this, if you add it to both sides, voltage of the battery equals voltage of the capacitor. Does that make sense? You betcha. Because if you think about loop rule still holds. Change in V equals zero. The voltage by the battery minus the voltage by the capacitor equals zero. This kind of makes sense, right? So that's why no more current flows through. Okay, so in that case, if you want this capacitor, so let's end off with this kind of concept. If you want this capacitor to get more current, like, so let's say it's fully charged. I should start with that. And let's say this battery is 9 volts. If you want more charge to be stored on this capacitor, what do you need? Well, you need that larger potential difference, right? If the potential of the capacitor is equal to the potential of the battery, no more charge is going to flow, so you need more voltage for your battery to get that potential difference. So I'll get this to 12 volts. So if I get this to 12 volts, now there's a potential difference again. This was at 9 volts. More charge is going to fill up until this is back to 12 volts. Well, now, if I change it to 15 volts, potential difference. More charge is going to charge onto the capacitor. This will become 15 volts. It'll get more. So the key idea that I'm trying to show is that more voltage will lead to more charge being stored. It's like that linear sort of relationship. Now, how do I show this next part? I'm trying to introduce an equation and try to make it make sense. That's why I'm just trying to think about how I would explain this. Here, let's explain it like this. Let's say you have a battery, and let's say this this capacitor has a certain area, and then I get the same battery, but this capacitor is much larger. And let's say they're both 9 volts. Now, this capacitor is larger area. You can intuitively imagine it's going to hold more charge. So for this 9 volts, let's say they're fully charged, this larger plate is going to hold way more charge, right? And hopefully that makes sense. But let's say now I change them to, let's say I change this one to 12 volts. Well, now there's more of a potential difference. I can kind of push more charges onto this plate. So now which one has more? It's like this one has a smaller plate, but there's more potential difference. So if I set this one to the same thing, 12, yeah, it's going to have more charge than this one, right? Because now they're at the same potential difference. So the capacitance of a capacitor depends on the area, but it's really like a ratio. C, the capacitance of a capacitor is equal to Q, the amount of charge it can hold over V at a certain voltage. So if I set them both to 12 volts, right? If they were both at 12 volts, the bigger one, so let's say this is same, right? Same 12 volts for both of them. So C1, C2. So Q1, Q2 over V. The V is the same, but this one gets a bigger charge. It has a bigger capacitance, right? If they're at the same voltage, this one holds more charge, so it has a bigger capacitance. That ratio is bigger. Now, let's say I increase this to 15 volts. If I increase this to 15 volts, the capacitance of this capacitor is the same, right? I'm not saying capacitance depends on V. It depends on the area and it depends on the distance, and hopefully you watch that video in class. But the capacitance is the same because it depends on the area, not the voltage. So if the capacitance is the same and I made the voltage bigger, the charge on the thing gets bigger. Because of this ratio, the capacitance is the same, right? So if I were to graph this, Q over V, if I think about C1, I'm going to make C1. I'm going to make this one like a full line. And then I'll make this one C2, which will be dotted. So as you can see, as I increase the voltage, I'm definitely going to get more charge on the capacitor. But let's say this is 12 volts, right? This is a 12 volts mark. C2 has lower capacitance, so its charge, the charge it holds, Q1, okay, I should be more consistent. Q2, right? Because this is C2. That Q2 is smaller than the same charge by C1, right? The same charge this one holds, it's greater at the same potential difference because its capacitance, its ratio is bigger. And this is a concept when I was learning this over the summer. I had to really try to wrap my head around this idea that capacitance is not really affected by the voltage, but it's like the idea of the ratio. Because as I get more voltage, I get more charge. If that still doesn't make sense to you, that's okay. I'm just introducing this new equations to you, and hopefully we can work together to make it make sense. Thank you for watching. Sorry if this was a long video, but hopefully this will clear everything up. Thank you.